Unit 4 begins right now with relating graphs to events. Now, we're going to be looking a lot at graphs for the rest of the semester, so today we're just kind of analyzing graphs that relate to real world situations and explaining what's going on. So, realize that each graph has two axes. There's an x-axis, which is the horizontal axis. So like in this first example here, example A, the horizontal axis right here, that's the x. And it also has a y-axis, which is the vertical axis, so the one that's up and down, which would be this one on example A. Now, in these situational graphs that we're going to be looking at, each axis has a label. Now, in the examples that we do, the x-axis will always be labeled time. So you're like analyzing how something is changing over time. The y-axis is what's going to vary from problem to problem. So it might say like altitude, like example A, total distance, speed, height. So that will change depending on the example, but the x-axis will be time. Now, before we analyze this first graph, and that's the first kind of part to this lesson, there's three parts really. The first is analyzing graphs, then you'll have to interpret a graph and then sketch your own. But it's all about graphs that are related to a real world situation. So before we look at this one that's talking about a trip to London, I want you to realize what you're actually looking at when you look at this graph right here. Because normally, you guys, the x and y axis looks like this. Okay, this doesn't look exactly like I'm used to with a graph. Now the reason that is, and most of you probably would know this, but you're only looking right here at what's called quadrant 1. So you kind of ignore the rest of the x and y axis, the rest of the graph. The reason that is because this first quadrant is where all the positive values are found. And that makes sense when we're talking about a real world situation because like I can't have negative time and I can't have a negative altitude or a negative height. It just doesn't make sense. So real world situations here when we're measuring something, I can't look at the negatives. So we kind of ignore all that and we just look at the first quadrant. So that's what this picture is here. And the first question wants to know, what's the graph showing? Well, there's a lot of labels going on at the different parts, kind of where the graph changes. Those are what we'll think of as like different parts of the graph. As a whole, though, this graph is showing a plane's trip to London, and it's showing how its altitude is related to the trip over time. So let's just say like the altitude or the height, how high the plane is, of a flight to London. Yes, you have to write for your answers here. I know, it's terrible. It's like English. Okay, so question 2 says, where is the plane going the fastest? Well, if I kind of look at what's going on here, you start right here at 0. And then you read it from left to right like you would a sentence. So as it's like someone starts the stopwatch and time starts. So, okay, here's what's happening. I'm taking off in New York. The altitude goes up. The plane's obviously like taking off and getting to its cruising altitude, which is what's happening right here at this part. Then the altitude goes down as the plane like kind of goes in for its landing. Right here, the altitude kind of levels off because we're circling as we wait for a runway. And then we finally land in London. So if the question's asking where's the plane going the fastest, well, I mean, I've been on a flight before, so I know that usually we're going the fastest when we're like cruising. But there's no way to say for sure, you guys, so don't let them trick you. The graph is measuring altitude, so I can't tell. It's not measuring speed, so I don't want to answer that question. I'm just not sure. Okay, so be aware of like what you are measuring as far as the graph goes. If it's altitude, I can't say for certain about the speed. But question 3 asks, where's the plane at its highest point? I can definitely answer that question because we're talking about height or altitude. So obviously where the graph is the highest is going to be the highest point, which is just all right here at the cruising altitude. And then question 4 says, what does the flat part of the graph represent? Okay, if you don't know what part they're talking about, it's the part that I just underlined actually right here. This is the flat part. It's like perfectly horizontal. Now that represents here that the altitude isn't changing. It's like staying constant. That's a good word to use. It's staying the same or staying constant as time passes. So the plane's not getting higher or lower. Constant speed, not speed. Constant altitude. Use the right word, that always helps. So I could say constant altitude or height not changing. Okay, so there's an example of analyzing a graph. Let's do one more. Graph B says we're talking about a commute home, so kind of like your trip home. And again, the x-axis is measuring time, like we said. The y-axis, though, that's the one that's going to change. This time, we're not measuring like my height on my commute home. We're measuring my distance, like how far I've traveled. So that's exactly what the graph is showing. It's showing my distance traveled on my commute home. So question 2 says, well, on this one, where's the person going the fastest, and how do we know that? Now, although this is not measuring speed, I can answer this question on this one, because if you remember from Unit 1, distance, time, and speed, remember the dirt problems? How could we ever forget, right? Distance, speed, and time, or rate, those things are related. So I actually can answer this question. And if you look at kind of the different parts, it even helps you do that. So like right here, this first part, the person's walking. So you just left school maybe, you're walking slowly, your distance is increasing like not very steeply. And the same thing's happening here. So if your distance isn't increasing very quickly, then you're probably walking slow. But see right here, the distance is a little bit steeper, so I'm traveling more distance over less time, and I'm on the bus, so that makes sense, but this is where I'm going to be going the fastest. Okay, so when I'm taking the bus, the reason I know that this is when I'm going the fastest is because I'm covering, or the person is covering a lot of distance in a short period of time. Hopefully you can read my handwriting on all this. If you can't, then you just ask me tomorrow in class. And I'm going to say, I know that because it's steeper. Okay, so if you're measuring distance, where the graph, the part of the graph is steeper, that's when you know you're going the fastest. Because short period of time, you're traveling a lot of distance. This one wants to know, what does the flat part of the graph represent? So here's the flat part on this one, right there, when it's horizontal. And I mean, they flat out told me, they won't always, but I'm waiting for the bus. So, okay, think about what you're doing when you're waiting for the bus. Well, you're stopped, you're not moving. And I know that because the distance isn't changing. I haven't covered any more distance, I haven't gone further, I'm just holding still in one place. Now, question 4 says, why does this graph never go down? Like the other one, the altitude, the plane eventually came down, the altitude decreased. Well, why doesn't my distance decrease? And if you think about it, I mean, if you're walking home after school, taking the bus, all that, whether you're walking forwards or backwards, you're covering distance. You can't like decrease in your amount of distance that you've covered. You're going to be walking further and further either way. So I'm going to say if the person's moving, then they're covering distance. If you're stopped, the graph's just going to be flat. But other than that, if you're moving, it's going to go up. You can't go back in time and decrease the distance that you've traveled. Okay, so that's the first part, analyzing a graph. They give you the situation, you kind of answer some questions. Now, the second one is maybe they give you like the outline and you have to go in and say what each part represents. Now, this is a little redundant because honestly, this looks exactly like this last question, except the labels aren't there. But essentially, that's what you're doing. You're going in and you're labeling what's happening at each part. So, like where the graph changes, those are the different parts. They told me the situation. It's a very interesting topic, I know. My trip to school in the morning. So, I want to explain what's happening during each section. Okay. The point of this, I know it looks similar, but it's just to practice kind of like making up something that makes sense. And that's the thing. If you just make something up that makes sense, you'll get the credit here. There's tons of different answers. Okay, so here's what I'm looking at. I've got time on the x-axis, total distance on the y-axis. So if I kind of like step back and look at this, I've got 1, 2, 3, 4 different parts I need to describe. And to me, and we kind of saw this on the last example, when the person was just like walking, these two parts look the same. So if you have that, you can kind of like double dose this here and do both at the same time. So let's say that I start here at 0. I'm driving to school in the morning. So obviously I leave my house and maybe I'm on like a country road. No, I'm not going to tell you where I live. Not going to do it. But maybe I'm driving on a country road. My distance is not increasing very quickly, so I know I'm not driving very fast. So I'm going to say distance increasing slowly, and I'm going to put in parentheses country roads. Not going to go as fast on those roads. Okay, the flat part of the graph, yay, right here. Honestly, the number one mistake people make in this lesson is they just mess up on what the flat part means. But I saw that last time. The flat part, when it's distance, means that I'm not moving. I'm not covering any ground. Okay, so maybe I got pulled over. Let's make it interesting. That's sad, because I was on a country road. I wasn't going very fastly. I don't know, maybe I had a tail light out or something. But I got pulled over. Distance isn't changing. I'm stopped. Okay, right here though, so I got pulled over. I'm freaking out because I'm going to be late to work. So here my distance is increasing really quickly. Not much time is passing and I've covered a lot of ground. So maybe I'm speeding. I would never do that, you guys, but maybe I decided to because I'm freaking out and going to be late for work. Don't judge me. Do a smiley face. And then I realized, ooh, I'm good on time, so I kind of slow down and I like ease my way into Homestead on Homestead Road and a Boyd Center, all those country roads we'll call them. Okay, so sometimes you might be given like the outline of a graph and you have to just kind of like explain what's happening at each part. So that would be like interpreting the graph, kind of like analyzing. The third part, though, to this lesson is sketching your own graph. This is a little bit different. So I want to sketch two graphs. One, and they both relate to the Top Thrill Dragster at Cedar Point. Hopefully you've been on that. If you haven't, you're missing out. But the first graph, I want to show the speed of the dragster. So this one needs to measure speed over time. And the second one needs to measure the height of the dragster over time. Okay, so you got to think about the ride. If you've never been on it, here's what they do. You just start like at a complete standstill, and then they just like out of nowhere shoot you so fast up this hill, and you go up this hill, and you like kind of ease over the top, and then you just come right back down. So it's like a really short ride, but the thrill of it is you get like shot out like a cannon. So if you're thinking about the speed, you start at 0, and you start at like a stop. You just go from like 0 to 80 so fast. So what's going to happen here is my speed just going to like shoot right up. Okay, so I'm going to represent that. Make it steep because not much time passes. You go so fast and it happens really quickly. At the top of the ride though, so we'll say, whoa, we got shot right up. at the top of the ride, you kind of have to ease over the hill. Honestly, and sometimes the ride doesn't make it. I don't know if anyone's ever seen it not make it, but sometimes it doesn't make it, and we'll say this one does. But you slow down to get over the hill, so you don't make it look like the roller coaster. That's what people think. They just want to go up and down. That's not true. It comes down because the speed decreases as you go over the hill, but you don't stop. Then eventually you just fly right down the hill. So you go really fast, and then eventually you come down to a stop. This is tricky. I'm going to put a star on it. Because when they talk about a roller coaster, you just want to go, oh, the hill. You want to draw the hill. But you have to think about the speed. Go really, really fast. You slow down at the top, and then you go down the hill, so you increase your speed again, and then eventually you come in for a stop. The height, that's going to be more like what you're thinking for the hill of a roller coaster. You start at 0. Okay, so the height, you start like low, we'll say like on the ground, if you will. And then it's going to just look like the hill, basically. So it happens quick, so we're going to do it over not a lot of time. But you go up the hill, you kind of like spend some time getting over the top, and then you just come back down. And then you stop. And your height is at nothing. So this is a little tricky. Speed gets a little bit tricky on these. Otherwise, hopefully, this is kind of a decent lesson to ease you into Unit 4.